Hi, welcome back to the second part of my lecture, and let's jump straight in. So we will be talking about the higher regularity of the surfaces that we've seen at the end of the first video, and this will be within this framework that I described before, the Hildebrandt von der Mosel framework for Cartan functionals. And in the second and third part of the talk, I will present to you the ingredients that we need to prove regularity results within this framework. Okay, so here's a result that was obtained earlier in 2013 by a previous PhD student of Heike von der Mosel, Patrick Overath, and this was done in the codimension 1 setting. So previous works have always been, in this Finsler case within the Cartan framework, have always been in codimension 1. And in 2013 they obtained this result where you have a disk-type surface and a Finsler metric on R3 and also the standard Euclidean metric on R3. And then given a certain condition, we know that every conformal minimizer is actually of higher regularity. So recall that on this conformality condition, this was already, this came out of this existence result, right? So if you have this existence result from the previous lecture, you get automatically that the minimizers can be conformally parametrized. And for every such conformal minimizer, we know that it's of one further differentiability. So W22, and the first derivative, the differential, is actually Hölder continuous. Now what is this condition here? Let me try and explain it. So for a fixed point Q, consider the function fq, which is a function on the tangent space at point Q in R3, and then also the Riemannian metric generates a norm. So f is a norm and the Riemannian metric generates a norm at that point Q. So these are both functions on the tangent space at point Q. And as such functions, you can consider the seminorm, the C2 seminorm of those functions, if you restrict it to the Euclidean sphere, right? So this is what that object here is. This is the seminorm, just the C2 derivatives, the second derivatives measured in the supremum norm. And this should be bounded by a universal constant for all Q, and then you get the regularity result. All right, so what I can obtain in my thesis is the following. Now we can do this in arbitrary codimension, and we get a disk-type surface in Rn, and also we get an arbitrary Riemannian metric on the target, and then for a universal constant which depends on the metric and also on the dimension, we get the same result, right? The analogous result, where we have to compare the Finsler metric, the Finsler norm, and the Riemannian norm on the Riemannian sphere in the tangent space at point Q in this C2 way. And so maybe an intuitive explanation of this would be the following. So this is a second order condition, C2, and basically you can look at the unit balls of the Finsler metric at point Q and the unit ball of the Riemannian metric at point Q, and these are just objects, and they will be submanifolds, and you can then look at the curvatures of those manifolds and compare the curvatures. And I haven't done this calculation, but I think this should be the intuitive explanation what this condition means, right? So you compare the curvatures, and the curvatures shouldn't be too far apart, bounded by some constant, and then you get this regularity result. So really, in a neighborhood of the Riemannian case, we get this regularity here. Okay, so what I really would like to do is the following. We substitute the target manifold to some arbitrary manifold and also some arbitrary Riemannian metric on that manifold, and we look at the corresponding condition in this sense here. So you take the sphere bundle in this arbitrary Riemannian manifold, and then you look at the C2 norm, semi-norm of the corresponding norms, and then hopefully you get the same. So I have some idea how one could do this, but I haven't worked this out, so this is not yet a result, but it's what I would like to have. Anyway, this is the result that I'm presenting to you in this lecture. So let me show you some of the ingredients that are needed to obtain such a result within this Cartan setting. One of the ingredients is the so-called perfect dominance function of a Cartan density. So let me remind you from the last video what a Cartan functional and its Cartan density are. So this was a function which gets a point in space and a bivector. So these were the partial derivatives of the surface, and then you wedge them together, and it should be positive one homogeneous, convex, and of linear growth. Linear growth, that meant comparability of this Cartan integrand and the classical area integrand. And I'm not sure I mentioned this in the first video. So this whole Cartan setting is a generalization of the classical proof of classical area minimizers. So an area integrand is an example of a Cartan density, as we've seen before, and what's coming next, the perfect dominance function, that will play the role of the Dirichlet energy in this classical setting. So in the classical setting, what you often do is you take the area functional and then you penalize it with the Dirichlet energy, and then you do a minimization of this penalized functional. And so there is a relationship within the area functional and the Dirichlet energy, namely that if the surface is conformally parametrized, they will be the same, and otherwise the Dirichlet energy will dominate, will majorize the area functional. So that's what the connection here is. In any case, here I'm going to present to you a theorem, namely the following. We get for every conformal minimizer the required regularity if the Cartan density fulfills two more properties. So one of the properties is that it's actually more regular than we needed, than we assumed, C2, but it should be better, should be C2, not C0, but only outside of the zero bivector, right? And the second one is a bit more obscure here on this slide. You need to have a perfect dominance function. So now the next two slides will be a bit more technical, but please bear with me. I'll explain to you what a perfect dominance function is. So here we go. A function, an integrand, is a dominance function if it is a function which takes a point in space and a matrix, n by 2 matrix. So this will be u and the differential of u, du. And it will be a dominance function of a Cartan density if it dominates the Cartan functional. So you take a matrix with two columns here, put it into P into D, and then you take the wedge product of these two columns and you plug it into E, right? So it should dominate the Cartan density, and also it should be equal on the set of which corresponds to conformally parametrized surfaces. So this is a conformality condition on the back here. And as similar to Cartan densities, we also need that in this matrix variable D, we need 2 homogeneity and quadratic growth. So you want to compare now the dominance function to the Dirichlet energy integrand, right? So the norm of p squared. This is quadratic growth. So this is a dominance function, and then on the previous slide we had this word a perfect dominance function, so that is the following. You need also in this case that the dominance function is C2 outside of the zero matrix. And before we go on, let me remark here that on the previous slide we had Cartan densities which were C2 outside of this zero bivector. And if you consider this in the space of matrices, n by 2 matrices, this is a bigger set. So the Cartan density has a larger singularity set, because if you have any matrix which has linearly dependent columns and you take the wedge product, automatically this will be the zero bivector. So here the dominance function should only be singular in the zero matrix, not in the set of rank 1 matrices. Okay? Whereas the Cartan density has a bigger set of singularities. Okay, and the last condition, let me maybe start here at the bottom. If you come from the world of gradient flows in metric spaces, then maybe you know what lambda r convexity is, or there they usually call it alpha convexity. And it's the following here, that for any radius, you have a constant depending on this radius, such that in balls of the given radius, you have that the function we're considering, so the dominance function, minus a multiple of the Dirichlet energy integrand is convex, right? So this function minus the classical dominance function is convex. This is that ellipticity condition. And if we wanted to, because this is C2, we could write this convexity as a second order condition, right? So take the second derivative and you get that some matrix needs to be positive definite. Okay, so now we know what this is, perfect dominance functions, and maybe now the question is, when do such perfect dominance functions exist? Under what conditions on E do they exist? And that's the content of this slide here. There's another theorem from early 2000 where given a Cartan energy, a Cartan integrand, which is C2, like before, outside of the zero bivector, positively one homogeneous and of linear growth with two constants, M1 and M2. And now we need uniform ellipticity of this integrand. And by uniform ellipticity, now I mean that there is a global constant which does not depend on a radius, such that the Cartan density minus a multiple of the area integrand is convex. So on the previous slide it was the dominance function minus the Dirichlet energy, and here it is the Cartan integrand minus the area integrand. That should be convex. And if that's the case, then there is a smallest number such that for all larger numbers we have we can create a new integrand which possesses a perfect dominance function, and this new integrand is the old integrand, and now it's plus a multiple of the area integrand. Okay, so that's what you can do. And maybe this is still not what we are interested in, because we start out in our case, in the Busemann-Hausdorff area case, we start out with a given functional. We don't want to construct a new functional. But thankfully, there is a corollary by Patrick Overath and Heiko von der Mosel in a paper in 2013, which says that if we are given a Cartan density as before, so that was a C2, positively one homogeneous and of linear growth and uniformly elliptic, and also we have another C2 comparability condition here. So again we have C2 semi-norm of the integrands now. So this is the area integrand and this is the Cartan integrand. This should be bounded by some constant which they give here in their paper as 1/5. Then the Cartan density itself possesses a perfect dominance function. And let me mention here already, maybe if you recall on the main theorem that I showed you a few slides back, there was a C2 comparability of the Finsler norms and the Euclidean and the Riemannian norm, whereas here this is a C2 comparability of the area integrants, right? So this would be, in our case, would be the Bussmann-Hausdorff area, and this would be the classical area. Keep that in mind. Okay, so the next ingredient that we need is a wonderful tool. That's the Radon transform. That's a tool from convex geometry. And, well, let me show you a slide of what we want to achieve before I introduce to you the Radon transform. Okay, so let me summarize what we had before. We are in the m=2 case, two-dimensional domain, and the target is Rn. And then we want to show that the integrand of the Bussmann-Hausdorff area, which was introduced in the last video, it should be C2 outside of the zero bivector, and it should be uniformly elliptic, and we should have this this C2 comparability condition. And I said this before, this is what we need for the corollary on the previous slide, and that is the condition that this should be small in the main theorem. And similarly to the existence result we saw in the first lecture, you can translate conditions on the Finsler norm to the corresponding area integrand. Okay, so that's what we're going to do now. And we were going to do this by means of the Radon transform. And to introduce this, let me make a motivation or a calculation for our integrand here. So we're going to look at, so this is from the previous lecture, right? So it's just a reminder. And we're going to look at this weight function again, or more precisely, we're going to look at the denominator. So the denominator takes the Hausdorff measure of a full ball intersected with a plane. And so what we're going to do now is we're going to look at that plane. And remember, we had an auxiliary Riemannian metric on the target space, and at point Q, that's a scalar product on the tangent space at Q, and we're going to restrict it to this subspace, right? So now we have an m-dimensional plane in the tangent space TQN, and we have a scalar product, which is just the restriction. Okay, so in this plane, we're going to use spherical coordinates, and then we can write this measure as this integral over the sphere times the integral over the radius of the characteristic function. And, well, we're going to first calculate the interior here. And maybe recall, this is easy to see, some point, so s is the radius and theta is the direction. So some point here is in the unit ball of the Finsler metric if and only if the radius is bounded by f of the direction to the power -1. So just take f of this thing here, that should be less or equal than 1, and then use the homogeneity of f and solve for s, okay? So now we can calculate this integral, right? Because it's not an integral from 0 to infinity, but just to f to the power -1. So that's what we're going to do. And this is just a very easy integral over s, so we can calculate this. And I've done this here on the next slide. So this integral here is just f to the power -m, and you get another factor here in front. And what I've done already here is I've divided by this constant from above, right? So here and here. And now what we're going to do is, well, this is an m-dimensional sphere, m-1 dimensional sphere, in this m-dimensional plane, which is a subplane of the full tangent space. And because it's just the restriction of the surrounding scalar product, G, This is just the same as the full dimensional sphere, Sn-1, intersected with that plane, right? Just because it's the restriction, so it's an isometry, this inclusion. Okay, so keep this in mind. So there is a mean integral over a sphere intersected with a plane of some function. And that's just the definition on the next slide of the Radon transform. So here it goes. The Radon transform is a function, is a linear operator, which takes continuous functions on the sphere and gives you a function on the Grassmannian, so the set of m-dimensional planes in Rn. And the definition is for the transform function you have to plug in planes, and it will just be as we've seen before. You integrate over the sphere intersected with that plane over the given function. And you need to be a bit careful here. This is not completely obvious why this should be continuous. Maybe you say, well, this is just integration of a continuous function, what can go wrong? And indeed, it's not very hard to show. I'll give you another result on the next slide, but this needs to be checked, okay? Nevertheless, by this motivational calculation that I showed you 2 slides ago, we have this corollary that our Busemann-Hausdorff area integrand is the classical integrand, and then you have 1 over the Radon transform of the Finsler metric to the power minus m, right? So we did this calculation earlier, and there was this integral, the S integral, and we calculated it, and it was f to the power minus m. And the plane that you have to plug in is the planes generated by this m vector. And remember, this was a simple m vector, and simple m vectors are in, or the projectivization of simple m vectors are in 1-to-1 correspondence with m-dimensional planes in Rn. Okay, so here are a few properties of the Radon transform. Oh, first let me mention that this is my opinion. So the downside to using just the Busemann-Hausdorff area integrand as we've defined it before is that in high codimension this space is not a vector bundle, right? So this is a cone bundle, an algebraic cone bundle, and this is my opinion. It's more difficult to handle this. And here, when you use the Radon transform, you have that each of these spaces, the sphere and the Grassmannian, they have a lot of algebraic and geometric structure. Namely, you have a Lie group which acts on them transitively, and so they are homogeneous spaces by that Lie group and a subgroup. And then you can do a lot of algebra and geometry and use good structures, right? And also, right. And, well, what I've written down here is not so important, but basically this Plücker embedding that I've mentioned a few times now, it relates the 2 spaces, these bivectors, these simple bivectors, and the Grassmannian. Okay, so here are a few properties. Here's the definition of the Radon transform again. And the, in my opinion, most important property that we need here is this ON equivariance. So I said this before, this Lie group, it acts on both the sphere and the Grassmannian. So I have a Lie group action on the base spaces, and then you automatically get a Lie group action on the function spaces just by precomposition. And the point here is that you have the well, you have this equivariance. So what does this mean intuitively? So here, let's look on the left side. Here we have to plug in a plane, and you take a rotation matrix Q, and that means you are going to tilt this plane, right? So you take a plane, and you tilt it by this matrix Q, and then you're going to plug in that tilted plane into the Radon transform, and you're going to calculate the integral over that tilted plane. But that's just the same as if you had just shifted the graph of the function originally by the same rotation, and then you rotate you integrate that that shifted graph over the original plane, right? So that's just the same. So if you tilt the plane or shift the graph, that's just the same. And that's the proof of this, right? And now this is very nice because now you can take this ON equivariance and you have this Lie group action here and here, and you can take the differential of that Lie group action. So take the differential with respect to Q at the identity, and then you will get the following result, which is differentiability result. You can show then that you have, if you're given a C1 function here, then also the transform function will be C1. So you don't lose regularity. And because you can do this calculation here, if you take the derivative with respect to Q at the identity, then you get this this infinitesimal version on the Lie algebra level. Okay, so it's not so important here, but what this means is it gives you a way of computing the differential of the transformed one into some direction by just transforming the differential of the original function to some direction. Okay, so that's what this is, and here I've copied it for you again at the top. And if you iterate this, then you can get the following result, namely that if you have a CK function, you also get a CK function on the output of the Radon transform. And moreover, as an operator between these Banach spaces, it's a continuous operator, and you can get explicit bounds for the operator norm. So that's here. So this is just an application of that result up there, and then you have to do kind of a long computation for these operator bounds when you take the covariant derivatives, higher order covariant derivatives. But nevertheless, you get that it's a continuous operator with explicit bounds. And the last result that we need is, maybe let me mention this. Probably this is known somewhere in the literature, because the literature on Radon transforms is quite extensive, but it was written in a language which was hard for me to digest. So this is probably known already, but I couldn't find it. And nevertheless, this one here, this theorem, is in this book by Helgason in the 90s, and it gives you that if you have the Radon transform and you look at even functions on the sphere, then this is an invertible operator, right? So if you restrict it to even functions, then you can invert this operator back. And why even functions? Well, because if you have an odd function on the sphere is symmetric. If you have an odd function on the sphere and you intersect it, then you will get a subsphere, and the function that you start out with was odd, so will still be odd on this subsphere, and then if you integrate it, it will integrate to 0. So the odd functions are in the kernel of the Radon transform. Okay, so you have these properties, and here is a summary of the results that we needed. We wanted to show 3 things. One was this C2 regularity, and for that we can use the higher differentiability of R on the previous slide, right? And why can we use this? I didn't mention this. Recall that we can write the Bussmann-Hausdorff integrand as 1 over the Radon transform of some function times this standard classical integrand, okay? And because it's 1 over this differentiability, it's 1 over the Radon transform, we can use the higher differentiability of R. And similarly, for the uniform ellipticity, you can now use the invertibility of R. At least in our proof, I don't know if this is the most straightforward way, but in our proof we do need to use this invertibility. And for this C2 comparability, here you can use also the higher differentiability and these explicit operator norm bounds. And yeah, that's that. And so again, this is my opinion. The main difficulty in high codimension is that this space here is not a vector bundle, and so you can't use this linear structure that you have in the codimension 1 case. And the benefit of the Radon transform, in my opinion, is that you can exploit all these nice algebraic structures which are quite rich and gives you a big toolbox. Okay, so that was my lecture, and I hope you have a lot of questions, and I'm looking forward to our Zoom session, and I thank you for your attention. Thanks for watching, and see you soon. Bye.